Okay, so this lecture will be about some examples of pressure sensors and microphones which are similar in structure to pressure sensors with some major differences. And the goal here is to let you know how we can actually make these devices using MEMS technologies that we've learned about so far, and maybe some of the differences between their capabilities. A lot of the examples I show here are relatively old. They're well established in the industry. There are some niche applications that use other types of structures from time to time. But vast majority of the well-established sensors in this market are covered by what we're going to talk about here. So when you look at the most common MEMS devices around you, pressure sensors are very near the top. And they have been among the most successful MEMS devices, microsensors in the industry, partly because of the need for them. We need pressure sensors in all sorts of industrial applications as well as automotive even you look at it historically, and nowadays in all mobile devices and elsewhere as well. And next to them, probably with increasing volumes, are accelerometers and gyroscopes, basically inertial sensors. RF MEMS is a category of devices which is gaining momentum more and more by the day. This used to be mostly about the resonators that you use to make, let's say, clocks and filters for RF applications, replacing devices that use the, let's say, SAW type of resonators with MEMS devices. Nowadays, you also are talking about relays and switches that are operating at RF frequencies. MOEMs are devices that manipulate light using micromechanical components, and you basically have an electrical interface in many cases as well. Most common example is the digital micrometers that are used in projectors. And there is a ton of other devices, right? But these are the more common ones that you see nowadays. Microphones, I put them next to the pressure sensors. It's a very similar type of a device. If you look at the segmentation, basically who is using these MEMS devices across the industry, historically automotive and consumer electronics have been there. Consumer electronics, especially with the advent of cell phones, has picked up, and that segment is growing. We are now putting more sensors into cell phones. We are also carrying other smart devices. Smart glasses were about for a while, now smart watches, and everything smart, right? And why do we call them smart? Because they can see what is going on in the environment. So they have sensors, right? There's no way about it. Otherwise, it's just a microcontroller, it's a computer. And you have to provide input to it to get some output from it. But a smart device interacts with the environment, and therefore it needs to have sensors in most cases, in all cases, and sometimes actuators. In terms of MEMS manufacturers, this is a relatively old graph, but the intent here is to show you that the sensor manufacturers are actually most of the top MEMS manufacturers nowadays. In recent years, RF MEMS producers have basically become closer and closer to the top ranks in terms of MEMS manufacturing, and that's again because of the widespread use of mobile communication systems, be it cell phones, be it IoT devices, and also the issue that the new communication technologies are operating at a larger number of frequency bands, therefore you need more filters, therefore you need an integrated system of more RF components. And RF MEMS manufacturers are creeping to the top of this list. Actually, they may have topped it already. And at the end of the story, nonetheless, a lot of the MEMS devices, when you talk about MEMS, most people that have some familiarity with the technology think about MEMS sensors, not RF MEMS necessarily. But as I said, RF MEMS obviously has a growing portion of this market. In terms of forecasts, again, you can see that when you look at this list, in terms of the type of devices, pressure sensors and gyroscopes and accelerometers and microphones constitute a good portion of this market share, and then RF MEMS is a portion that is getting more and more momentum. Now, how do we make a MEMS pressure sensor? The simplest device that we can think about when we think about measuring pressure is to make something that deflects in response to pressure. And then if it is a ambient pressure that we want to measure or something, we want to have a sealed membrane, for example, in one instance. This sealed membrane, edges sealed, is held on top of a, let's say, chamber with a known pressure. If the pressure on the other side of the membrane changes, the membrane will deflect upwards or downwards depending on that pressure. So this is one way of doing it. This is an absolute pressure sensor. So at the bottom of that membrane, I can have vacuum, or I can have some known pressure and maintain it. An alternative to have a differential pressure sensor, where you measure the pressure difference between the two sides of the membrane, and then the backing of the chamber here is open to your reference pressure, which in this case you can change, right? So you can, in this measurement, the goal is to measure the pressure difference between the two sides of the membrane. Tons of applications for pressure sensors. For instance, you measure pressure with them, right? So that on its own has a lot of applications in industry. Whenever you're manipulating gases or fluids, you want to know the pressure in most situations. Besides that, you can measure altitude using pressure. And then the modern MEMS pressure sensors that are out there are so sensitive that a half a meter pressure height difference, or maybe even less, a foot height difference, will give you a different reading of pressure. And that's amazing. You can actually easily use it to figure out on which floor of a building you may be without knowing anything else. You can measure flow, right? So in many cases, the flow can be measured by looking at the pressure difference between two segments of a microfluidic system, for example, based on Venturi effect. You can measure level in a, for example, fluid tank. The pressure that is applied to the bottom of that tank is proportional to how much fluid you have in that tank. You can measure leakage in a system, again, based on a pressure drop, for example. You can measure contact. A lot of the capacitive touch sensors are essentially, you can think about them as pressure sensors, right? So they're measuring pressure, and then for that pressure, for example, can be used to read the fingerprint on your fingers. At the macro scales, the pressure sensors that are made are based on a number of different physical phenomena. For example, you can have the liquid column pressure sensors, which again, you can see the operation here. You can have hydrostatic pressure sensors. Again, you have a bent column here. If the pressure here changes, the needle will move to the left or right depending on whether the pressure is increasing or decreasing. Ion gauges are interesting pressure sensors. In this case, you produce ions, and then you have an electrode that is collecting them. How much of those ions you collect is a function of and ionize. How much of the gas in the environment you ionize depends on the pressure. And all in all, the pressure and temperature sensors are probably the most common industrial sensors out there. And maybe next to them will be magnetic sensors in terms of application. So the market is huge, and for that reason, people since the beginning of MEMS development have tried to come up with good designs for pressure sensors. The basic design is applicable where we have a membrane and we just monitor the deflections of that membrane. We can do it, for example, in two ways. In one case, we can have a piezoresistive pressure sensor where we put the piezoresistors around the edges of the membrane, create a cavity underneath with a known pressure inside it, and when the membrane deflects due to the changes in pressure at the top, you measure the stress in the piezoresistors and convert it to the pressure changes. Alternatively, you can have a capacitive pressure sensor where, again, you have a flexible membrane on top, but instead of measuring the stresses that you produce in that membrane, you measure the changes in the gap between the two electrodes, the top one being a soft one that responds to pressure variations, the bottom one is your fixed pressure electrode. And again, you get a DC, or change in capacitance, that you can measure and relate back to pressure variations. The device, in this case, unfortunately, is inherently nonlinear, right? So you have two sources of nonlinearity. First of all, your membrane doesn't move up and down as a flat plate. You get some curvature to it, so the change in capacitance with pressure, you get some nonlinearity there. But also, it's a change in gap that you have. And then remember that the DC over dy, when the gap changes, is inherently nonlinear. So there are two contributing factors to nonlinearity here, but capacitive pressure sensors nowadays are becoming more and more common, and that's because we basically can get rid of the piezoresistors on the left side, which could be an additional or maybe two additional microfabrication steps if we can get rid of them. Membrane deflections can be measured in other ways as well, including resonance and optical methods. I'll talk about a couple of resonant pressure sensors in a second, but the capacitive and piezoresistive ones remain the dominant methods. Piezoresistive historically has been the more common type of pressure sensors, but new ones are mostly operating based on capacitive sensing. So here is an example of an early pressure sensor, piezoresistive. You can see that I have placed, or they have placed, 4 piezoresistors on the 4 corners of this chip. A membrane is produced here. You have 2 types of piezoresistors. Remember, we could have longitudinal and transverse stresses applied to piezoresistors, and you could get differential sensing if you put the longitudinal ones like here and then transverse ones here. And because pi L and pi T usually had negative or opposite signs, you could get a differential sensor out of this. And then we put it in a width and range arrangement like this to measure changes in resistance. We'll talk about this in the interfacing section in a couple of weeks. You can have piezoresistive pressure sensors that are made like this. This is a 4-inch wafer. You see all the membranes made on the other side. You see the characteristic anisotropic etching using KOH or TMAH. That profile tells you what that was. And this is the membrane that we realized on the other side of the membrane wafer, and placed the pressure, the piezoresistors around the edges of that structure. So same device, piezoresistive pressure gauge. Now the only difference here is that in this case they actually even took advantage of the stress distribution around the center of the membrane. So as your membrane deflects, you get the maximum stress around the edges of the membrane as you have the contact to the substrate, but also you get a lot of stress close to the center of the membrane. And in some cases, you know, if you have access to that location, you can place your piezoresistors there to measure that stress instead of the one around the edges. Here is a surface micromachine pressure sensor, piezoresistive again. Again, I realized a cavity down here. This is through additive techniques, so I deposited the membrane material on top of a sacrificial layer, then got rid of the sacrificial layer through an edge hole here, and then I have to plug that hole to maintain the reference pressure in the background. But in this case, I can use, for example, polysilicon piezoresistors to measure the deflections across the, or the stresses in the membrane and relate them to the pressure variations. So these are membrane-based pressure sensors, but there are other ways. And one of the simplest pressure sensors that you can make is a Pirani gauge pressure sensor. Very, very simple. It's ingenious design. The idea is that if you have a resistor and you hold it in a gas and you pass a current through this resistor so that it heats up, the only heat loss mechanism here, let's say the one that we want to focus on, is the conduction or convection to the gas. So conduction through the gas or convection by the gas, right? So you pass a current through this, you lose some of the heat through the anchors, so we ignore that part, so the substrate and all that, we ignore that part, but we lose some of the heat to the gas, to the ambient gas, through conduction or convection as well. And after a while, things become stable, right? So you basically raise the temperature somehow, then you lose some of that heat, and you reach an equilibrium at some point afterwards. Now, if the pressure in the environment changes, and in this case, let's focus on conduction, your conduction will drop. The gas conduction will become less if the pressure is reduced, for example, right? You will have less gas, therefore the conductivity, the thermal conductivity will go down. And therefore the equilibrium that you had before will not be there anymore. Your conduction is lower, your heat loss is less, therefore the temperature of your resistor will go up a little bit, okay? So that's a Pirani gauge. You have a heated resistor. If you can measure the temperature of that heated resistor, for example, you can put a temperature sensor very close to it. And if the pressure in the environment changes, the temperature sensor will read a different temperature based on the pressure. Now, the ingenious part of let's say the most simple Pirani gauge is that they mix both functions into one device. Resistors, if you remember, in most cases have a temperature coefficient of their own. So the resistance or the resistivity of a material is a temperature dependent property. So if you heat up this resistor, you can estimate the temperature of the resistor by monitoring its own resistance. So in this case, you use a resistor as a heater, you also use it as a temperature sensor at the same time. Of course, the electronics will be a little bit involved, but with just a single resistor, you can estimate the pressure inside an environment. Pirani gauges are very popular, at low pressures especially. They don't work that well at high pressures. You need a significant change in thermal conductivity in order to measure the change in resistance. And these are examples of Pirani gauges. So for example, this is your heater here, and then I've put a temperature sensor in terms of a thermistor in this case, right? Just the change in resistance of that will tell me temperature here. So that's going to be one example of a Pirani gauge. Here is another example. I have a heater. In order to reduce the amount of heat loss to the substrate, I elevate the heater from the substrate, detach it from the substrate, and make sure that all the contacts from the heater to the substrate are through bits and pieces that have a high thermal resistance. So that's one other type of pressure gauge. Pirani gauges are quite common, especially for the measurement of low pressures. Another type of a pressure sensor, this was actually one of the early examples of a successful MEMS product, are resonant pressure sensors. And I show you two examples. This is from early 80s. Early 80s it was designed. By late 80s it was a product that they were selling it. The way it works is that, again, you see these two heels that tell you how it was made. These are made using an isotropic etching of a substrate. This is the top side, the bottom side of a membrane. So you have one membrane that is exposed to a pressure that is changing. On the top side, the other side of the membrane, you have these two little heels. Now, what they did is that at the top of those heels, you have a resonator. So the structure you see here is a resonator. It's a massive spring system. They put these resonators on top of an electrode arrangement like this, and they make them vibrate. So those two resonators, these little pieces here, vibrate in and out of plane. Now, remember these two heels are made on the membrane. So if you have a pressure increase here, the membrane deflects upwards. These two heels will go, the top of these two heels will move further from each other. You apply a tensile strain on these springs here, and your resonant frequency goes up. And therefore, by measuring or monitoring the resonant frequency of that structure, you can estimate how much the pressure was. Doesn't look like a simple device to make, but for a good decade or so, this was one of the more accurate pressure sensors out there. And then, the package device looked like this. That includes a JFET or a transistor to amplify the signal from this device right there inside the package. A similar concept, again, a resonant pressure sensor, but with a different transduction mechanism, was developed in Japan. The first one that I showed you was developed in the UK. So in this case, what they had is, again, a membrane, and on this membrane they put an edge-shaped structure. What they did is that they passed the current through one arm here, a DC current, and put a strong magnet underneath this structure, so Lorentz force would push this device left and right, this arm left and right. On the second arm, they measured the voltage that was produced. Remember that if you move this inside the magnetic field, you get an EMF. So they measured the voltage that was produced across this second arm as an indicator to monitor the resonance, right? So they could close the loop. They could close the loop through an oscillator, pass a current here, measure the voltage here, go back through this loop. And by doing that, they could, remember at resonance we have the maximum response. This would lock to the resonant frequency of this structure. You had a constant frequency at the output. If you apply the pressure from the bottom, you would basically stretch this end and this end. You would move them apart from each other. So you would put a tensile stress on this structure, and therefore the resonant frequency would go up, and your oscillator would detect a higher or lock to a higher frequency. The device was made through a very interesting fabrication process, but at the end of the story, to just keep it short, this is the cross-section of one of these beams. They created a small vacuum chamber for that beam. So this beam was operating under vacuum for increased Q. The fabrication process was fairly complex, but at the end of the story, and then they had to sell a magnet with this device for whatever pressure sensor that they needed to sell. They needed to sell a permanent magnet with it as well. But again, this was a successful commercial product back in the 90s, and they sold, I think, a good number of them. Now, because pressure sensors that we make using MEMS technologies can be small, you can have an array of them. And then why do you need an array? Well, now you can detect pressure gradients, which can tell you about the flow. And in this case, I think this was an array of about 1,000 pressure sensors produced right next to each other, so that you could talk about the flow or direction of pressure distribution. Packaging of MEMS pressure sensors, obviously you need connection to the outside world. You need to see the pressure changes. So you need a vent, you need a hole on the package. That makes it non-trivial. You basically have to have this contact to the outside world. But this is a fairly common property of any pressure sensor that you see out there. You see a vent that goes into the package to let the sensor inside see the pressure variations. Now, pressure sensors are usually responding to something relatively slow, right? So you're monitoring the pressure of the environment throughout the day. Or, for example, if I'm going up and down stairs, the pressure sensor inside, let's say, my smartwatch is trying to figure out what is my altitude based on the changes in pressure. But that, again, is a relatively slow process, right? A microphone is doing the same job. So what we're doing with a microphone is that when we have sound in an environment, there is an acoustic pressure. This acoustic pressure comes and hit the, for membrane-based microphones, will hit the membrane, and the membrane will start to move back and forth. If we detect those movements, we can estimate the acoustic pressure intensity, right? So when you talk about microphones, structurally they are in most cases the same. You have a membrane that is deflecting in response to an acoustic pressure, and you measure that deflections, right? So in case of microphones, because the pressure, the acoustic pressure is usually much, much weaker than what you expect in, let's say, DC pressure measurements, Capacitive sensing is good enough. We don't really need piezoresistive sensing. You're measuring micropascals or millipascals at most, but it's usually on the order of micropascals of pressure change, versus a pressure sensor may measure tens or thousands or even tens of thousands of pascals in pressure variations. Silicon microphones are growing in market size, and again, the advantage they have over a traditional microphone is that you can make them smaller, you can make more of them at a cheaper cost, but also you can make them right next to the electronics. So in this case, all the electronics that you need for processing the signal from the microphone can be integrated with it and be sold to you as one package, where you only read, let's say, digital data out of that package, out of that microphone. With traditional microphones, you cannot do that. You can see that the market size is growing very rapidly. In 2020, it was $1.2 billion, and the driver behind it is, the earpods that you're using, or the cell phones, the laptops. All of these devices nowadays are using MEMS microphones instead of the traditional electret microphones from the old days. So, as I said, this is again a relatively old document. I think this is from 2016 or 2017. This slope has actually been more. The number of devices that are responding to your voice signals now is increasing. It is from all these big companies that are, let's say, Apple, Google, Amazon. They all have voice-activated devices out there. All of them have microphones, and usually it is more than one microphone. Even a simple earpod that you use nowadays has, in many cases, more than one microphone, so that you can compensate for the noises and sounds around you. So how do they work? Well, one question I have to you, and I'd like you to think about it as we go through these slides, is what is the difference between a pressure sensor and a microphone? So we said, the range of numbers is different, right? With pressure sensors, you measure pascals or tens of pascals. With a microphone, you measure micropascals. But what is the other difference? Well, pressure sensors measure very slow signals. You're talking about DC. Microphones, you're measuring tens of hertz to maybe tens of kilohertz. So these are fast AC signals. And what else is there? Well, if you think about it, I don't want my microphone to respond to the changes in ambient pressure. So I don't want, let's say, my microphone to behave differently here than on the second floor of this building. How do I do that? How do I make sure that the device that structurally is very similar to a pressure sensor does not respond to DC pressure changes? Think about it. You will see the answer in coming slides. If you want to check your answer, talk to me during the live lectures. But here is a microphone from Knowles. This is a market leader. I really don't follow the relative, let's say, portions of the market for each one of these manufacturers, but it has been a major producers of MEMS microphones. And in this case, what they have is a MEMS microphone. The microphone chip is separate from electronic chip. So they make the MEMS in one process and electronics in a different process. And this is the vent, where the vent is. And this is how it looks like if you just remove the cap from this package. So the MEMS microphone obviously has to be exposed, but the electronic chip, you can just put a bit of epoxy on it so that it is nice and stable. So this is a microphone from Knowles. These are different generations of microphones from Knowles. As you can see, this is the MEMS microphone, the capacitive type. As you can see, the membrane hasn't changed. The actual device, the part that is responding to your signal, hasn't changed over the years. Over the past, these three generations that I'm showing you here, this has stayed the same, but they have tried to reduce the dimensions of the chip from somewhere around 1.6 by 1.6 to 1.1 by 1.1, basically more than a factor of 2. Why do they do that? Well, now for the same kind of a sensitivity and device and everything else that they know, they make twice as many on the same wafer. They make twice as much money on the same wafer. And one of the reasons that they may not want to change the microphone, the mechanical design that much, is that they probably have invested a good amount of money on the electronic side. As long as the mechanical side doesn't change, the electronic side doesn't have to change either. So you can keep the electronics the same, improve on the mechanical side, at least the die size area, because the electronics is coming from a foundry like TSMC or SMIC or whoever. This mechanical part is where you are making, what you're making. So keep the mechanics the same so the electronics doesn't have to change, but try to make it smaller and smaller as you can so that you essentially reduce your cost per device and hopefully profit margin, increase your profit margin. Akustica is an interesting device, is an interesting company. They were one of the pioneers in MEMS microphone industry, and one of the advantages that they had over other competitors was that they made their membranes, their microphones, in a standard CMOS process. So the electronics and the microphone was made side by side. To make the membrane, what they did is again an interesting device, this interesting design idea. They used the metal layers in your CMOS process. The metal layers are usually between dielectrics. So they created these patterns of these metal layers such that you could get a more or less a membrane-like structure, released the membrane by removing some of the silicon underneath, and created the membrane that responded to pressure sensors. So here is an example of a device. So this is where you have all the electronics. In the middle of the chip, you created those structures. Let me show you a close-up view. This is made by patterning the metal layers in this kind of a configuration. And the reason that they're doing it like this is that so that they release the stress inside that metal layers. Remember, for CMOS, the stress in the thin film is not that critical. The films are all attached to the substrate, nothing is released. But if you want to release those metal layers at the end of the process to create your membrane, you need to find a way to let them release the stress without pushing the membrane up and off the page by too much. So this is what they did. So they create these metal structures and create the membrane. They send this for fabrication, get it back from the CMOS foundry. At the end of the process, they go and remove some of the silicon underneath using an isotropic etchant to release the membrane. So by doing this, they can do all the fabrication at the CMOS foundry other than last release step. So the device comes back, electronics is already there. You just create your membrane or release your membrane and you have a microphone. It seemed like a great idea. They were very hopeful that they could capture the market very quickly. Unfortunately, as it is usually the case in MEMS, it took them a while to ramp up production and reduce the cost and improve the reliability, probably much longer than they were hoping for. But nonetheless, a very interesting design approach and a pioneering design approach. So that's that for the discussion on pressure sensors and microphones. The next topic will be accelerometers and gyroscopes, and then I'll talk about a few other devices, mainly, especially RF MEMS components that we are seeing more of them these days. And that will wrap up the discussion of the devices.